Okay, hi everyone. So I'm Cindy. I'm from Columbia. A little caveat: this is the first time I've given this talk, so bear with me if like something gets confusing. It's like not you, it's me. So feel free to ask. This is you guys are the guinea pigs. So this is some work I did with my colleagues Fiona Skerman at Uppsala. Alex Wein at UC Davis and Dana Yang from Cornell. We did this work actually while we were at the Simons Institute about a year ago, so a big thanks to Mr. Simons if he's watching the YouTube video. Okay, so all right, so what I'm going to do is talk about this question about counting communities versus detecting them. And so to do this, I'm going to start by just going through kind of some simple community detection type problems that we know a lot about in order to kind of set the landscape. And then I'll start talking a little bit about the problem that we actually solved. And then I'll discuss a bit the proof. We use a class of restricted algorithms called low-degree polynomials. And I think kind of one of the cool pieces of this work is that I think we can make an argument that you can kind of, using the low-degree polynomial framework, you can solve sort of hardness of recovery problems by looking at equivalent testing problems and solving the hardness there. So I think there's a cool contribution about just the phase diagram for counting, but then also kind of the proof method I think is interesting in and of itself. I will mention, my colleague Alex is he's an expert on low-degree polynomials. He worked in this, a lot during his PhD and postdoc and these sorts of things. So it was awesome to learn from him on this project. Okay, so I wanted to start just talking about one of our classic problems, which is planted clique. So the planted clique problem has the following form. So there's two parameters, right? So I have a total number of nodes n. So in this graph, there's 16 nodes, n is 16. And I have an expected number of nodes in the planted structure. So here, k is approximately 5. I'm randomly selecting nodes with some probability, k over n in order to be in the planted structure. So k is the expected number of nodes. And so in the planted clique problem, all of the nodes in the planted structure are fully connected. So if we think about construction, you look at each of your n nodes, you say, is it in the clique or not with probability k over n? And then for the folks in the clique, right, they get a fully connected subgraph there. And then otherwise, we'll just think about, the background noise edges connecting two nodes outside of the clique with probability 1/2. Okay, so a classic question, right, is when can we recover this hidden structure? So if I just see the adjacency matrix of this graph, can I figure out which of the nodes are the red ones in an efficient way? Okay, so what do we know about this problem, right? So one of the things we know is that if it's just a straight up Erdős-Rényi graph, so if there's no planted structure, then there's going to be there's probably a clique there that's going to have size about 2 log n. So if there's no planted structure, but it's just a random graph, with high probability, we're going to have a clique of about this size. So kind of what this suggests, if we think about finding a planted clique, right, is that if the size of the planted clique is smaller than, the size of the clique that would just be there in the Erdős-Rényi graph, we aren't going to be able to figure out which nodes are in the planted clique, right? So for this problem, that's an information theoretic limit. If, our planted structure is, smaller than kind of the background random structure, we're not going to be able to find it. But, an interesting question is what can we do in this regime where we at least believe it's possible to find the planted structure? So kind of the dumbest thing you can think of to do, right, is just a brute force search. You search all, approximately k-size subsets of the nodes, and then the first clique you find, you call that your estimated structure, right? And if, k is a little bit bigger than 2 log m, 2 log n, sorry, the size of the random clique, right, then we'll be able to find it with this brute force search, right? So the stupidest thing you can think of, it'll work with probability tending to 1 when the problem size gets large, as long as our planted structure is large enough. But of course, there's a problem with this brute force search, right? Searching over all n choose k subsets of nodes is computationally intractable, and so when the problem size is big, this isn't actually a solution. So of course, there are many ideas about what we could do to find the clique more efficiently, right? So just something simple like degree counting is going to work if the planted structure is, like root n log n. Some more sophisticated methods like spectral methods have the same sort of success location, and semi-definite programming gets us at like root n. So what all of this suggests for the planted clique is that we have kind of a statistical computational gap that looks like the following, right? As we change the size of the planted structure, relative to the size of the entire graph, we see 3 defined regions where it's, information theoretically impossible to find the clique, where we think it's, it's possible, but it's hard, right? We don't know how to do it in an efficient way, and then in a regime where it's easy. Okay, so right, so this is what we're all here for, right? We love statistical computational gaps. Planted clique is a classic one. So for these sorts of average case problems, we have a sense of kind of rigorous evidence where these computational gaps exist, right? So even though what I said is I drew this line because it's like I said, well, we know all these methods like spectral methods, semi-definite programming, that the success boundary is here, right? And it turns out that our rigorous evidence for proving these computational gaps is, well, for the most part, just looking at large classes of algorithms and being like, okay, they all fail or they all succeed. And so there's a number of kind of restricted classes of algorithms that folks study to learn about computational hardness of problems, including like sum of squares algorithms, approximate message passing, like Andrea just mentioned, and what we're going to talk about, low degree polynomials. So kind of the idea of low degree polynomials is, if you consider all possible polynomials of degree less than like log n, let's say, and they all fail, then what we're going to say is we believe the problem to be computationally hard, right? And at some high level, the reason for this is because a lot of the algorithms that we know work efficiently can be formulated as low degree polynomials. So especially things on like planted clique and problems like this, all of our kind of subgraph tests where you count edges or triangles, these are low degree polynomials. Spectral methods fall under this umbrella. Andrea and Alex, in fact, have some work showing that AMP and low degree polynomials are kind of equivalent classes as well. So, okay, so what we're going to do is we're going to use this framework to study a slightly more complicated problem than planted clique. And this problem is just the planted dense subgraph model. So it's basically planted clique, but now instead of having all of the edges in the clique, we have a planted structure where they have some elevated probability of connectivity, right? So in particular, this is the model I'm thinking of. So now we're going to have 4 parameters. So we still have n and k, where n is my entire graph size. K is the size of my planted structure. And so for just a single planted dense subgraph, what do? The first thing we do is we look at all the n possible nodes, and then we flip a k over n coin and determine whether or not they're in the planted structure. So the idea is we'll have approximately k nodes in the planted structure, and then we're going to get data, right, in our adjacency matrix that corresponds to whether, two nodes have an edge between them. And so the idea is if both of the nodes are in my planted structure, so if their vertex labels are both 1, they get an elevated probability of connectivity, right? It's Q plus S, and the background noise is just a Q connectivity. So, okay, so folks have studied this problem for a long time, and there's, kind of two main questions that people seem to be interested in. And so the first is just detection. So the idea is, okay, if I have my adjacency matrix Y, can I do a hypothesis test and say something about whether, my adjacency matrix was sampled from this model or whether it's just, kind of from a null model that would just be a Erdos-Renyi graph. And then the other problem that people are interested in is recovery, right? So given that we have a graph that comes from this model, right, can we actually recover the nodes in the planted subgraph? And so, okay, so just to make this a little bit more formal, let's think about like the hypothesis testing problem. So, this is the detection problem, right? This says is Y sampled from this model or not, right? So what do we have is our null is that Y just comes from this background Erdos-Renyi, and our alternative is that we have the planted structure there, and then the challenge becomes the following, right? So as the size of our problem grows, so as the size of my graph grows, for what parameters can I find a test such that asymptotically the type 1 and type 2 error go down, approach 0, right? And so the two parameters now are going to be the size of the planted structure. That was kind of the one parameter in the planted clique. And now I have this other parameter that measures the strength of the elevated signal, right? And so kind of when you think about detection, when you think about hypothesis testing here, this is kind of the question we're asking, right? Can we talk about parameter regimes, for kind of size of the planted structure and the signal strength, such that there exists a test that we know that, vanishing type 1 and type 2 error. And, importantly, right, can we do this in a way that is computationally efficient? Okay, so folks know the answer to this, right? Many people have studied this. I'll mention this now. I did not write all of the references on my slides. I could not figure out a way to do it without making the slides look totally crazy. There's no references here, but they're all in the paper. A caveat. Okay. So the landscape looks like the following. So here, what I'm going to plot on my x-axis here is the signal strength, right? So on the previous slide, I have these two parameters, right? And so these are the parameters that make up the axes of these phase diagrams that I'm drawing. So the x-axis here is the signal strength, and as it goes this way, the signal strength decreases, right? So the problem gets harder. The y-axis is going to be the size of the planted structure, and as it increases, you get a bigger planted structure, so the problem gets easier. So in particular, for these phase diagrams, like kind of top left is the easy problem, right? Bottom right is when the problem gets hard. So here, I'm relating K and lambda, so the strength of the signal strength lambda and the size of the community K are both, some polynomial in N, right? And so what we're plotting are kind of the coefficients on that polynomial. So in particular, when beta equals 0, this says the signal strength is 1, which just gives me my planted clique problem. So what I have on the axis here, right, is just, this is the planted clique problem that we looked at before, right? This corresponds to the size k equals root n, right? When we're above k equals root n, semi-definite programming, these sorts of things work. When we're below it, we think the problem is hard because a brute force search works, but we don't know how to do it efficiently. And so, okay, so now this is planted clique phase diagram. Now we want to look at, planted dense subgraph phase diagram. And basically the landscape looks like the following. So if we're just interested in detecting, so just, kind of testing between a graph with a planted structure or an Erdős-Rényi, then we have a phase diagram that looks like the following. We have a big, easy regime, kind of a slice that's hard here, and then a space that we know things are impossible. And the same is true if we look at the recovery problem, right? But the shapes of the phase diagrams are slightly different, right? And in particular, what this shows us, right, is that detecting the planted structure is easier than actually recovering it, right? Because if you kind of like put this hard triangle on this graph, right, it would be over here. So, in detecting, all of this area is easy, which, for recovery, that's either hard or impossible. So here, detecting is strictly easier than recovery. So kind of what motivated our work was the question, like, all right, so if we look in this regime where we know that we can, detect whether or not there is a planted subgraph, but we don't know how to recover it in an efficient way, our question is sort of like, can you gain any information additionally about the planted structure? So, what we were thinking at first, like, can you learn the size of the planted structure? What we end up analyzing is, can we learn how many communities are actually in the planted structure? But kind of the motivation was, where we see this gap, what information is learnable, kind of as a go-between between the formal just detection problem and the ultimate recovery problem. Yeah.
Two short questions. First is that, what is the intuition behind defining the signal strength?
I think that this is just classically how folks have viewed these sorts of things.
Right, but it also comes up in many algorithms from the upper bound setting. You always get bounds based on these kind of signal string multiplied by something. So I was just wondering if there is a reason in the low degree tests or low degree polynomials that this kind of come up.
I don't know I don't know if it's from low degree tests generally, right? But kind of at some high level, right? SNR is always one of the things.
And another thing is that, what is the easy, is there a very simple method for the detection? For recovery, like you said, semi-definite. So what is the simplest method for detection that covers this easy part?
I think edge counting just works, yeah. Right, so, I count the total degree, and I think you can detect. Okay, so, right, so our question, right, is the following. In this regime where, recovery is hard, but detection is easy, might it still be possible to learn something about the community structure? And this is what we tried to formalize. So what I'll do is I'll just show a kind of toy example. I think it's the easiest version to understand. You'll get to see our results informally, and then I'll state them in all their mathematical glory. So, okay. So here's the toy problem, right? So I want to test between a graph with one planted structure, so one community. The size of the structure is going to be roughly k, and the connection probability within the structure is 2q. And I want to test that against my null or my alternative hypothesis that says there's two communities, each of size k over 2, and connection probability of 3q within the two communities. And so, okay, so how might we test, right? Well, the first thing we might do is just to try to count the edges, right? This is kind of the stupidest idea, right? But I've set up the problem such that this doesn't work. So, the way that I chose this edge connection within the communities is such that the expected degree is exactly the same for both graphs. So if you just think, so I did the calculations here for a node within the community. You can do the same thing for a node outside of the community. In both graphs, we have approximately k that are within community and approximately n minus k that are outside. So, kind of just to, how do I get this number? So it's like on, this graph, if I'm a node in the community and I want to look at, my expected number of edges, right? Well, there's n minus 1 other dudes I could connect to, right? And then the probability of connecting with any other node is the following, right? With probability k over n, they're in the community. Edge probability is 2k. With probability 1 minus k over n, they're outside of the community, and my connectivity probability is q.
So in this case, I can still count triangles.
Yes, and that detects. Yeah. And then, you do the same, you play the same game right now, probably of, you have to be in the same community to get the 3Q. If the node's in the other community, then it's just the Q background noise and so on, right? Okay, so, right, you guessed it. How do we detect, right? We count the triangles. And so what this shows is, that this'll work. So basically, under P and Q, the expected number of triangles in both cases is some constant times, Q cubed times K cubed. And then the variance of the triangles in both cases is of the order n cubed Q cubed, right? And so what this means is that, if these means are scaling at a different rate than my standard deviation, right, I'm going to be able to detect, right? And so, this sort of success statement then boils down to kind of a relationship between, K, Q here, which is my signal strength, and then the size of the entire graph, right? Okay, so then, but kind of the interesting thing here is that this success condition, so this success condition that requires, qk squared over n to grow, relative, to be larger than a constant, let's say grow in some way, this is the same barrier that we saw for recovering the planted substructure. So in particular, what we've shown now, right, is that doing kind of a simple triangle counting argument gives us the same easy regime as recovery, right? And so kind of the takeaway here is, in this entire regime where recovering the planted structure is hard, triangle counting fails to tell us whether there are one or two communities, right? So if we can't recover, then at least here triangle counting does not work either, right? And so informally, kind of the result we give is that if Q times, k squared over n is upper bounded by 1 over some term that's polylog and n, then no degree test succeeds at testing between the planted and the one or two planted communities, right? So we showed that triangle counting fails outside of this regime, and what we prove in the paper is basically that any polynomial test of degree less than log n is going to fail outside of this regime as well. Okay, so what I'm going to do, kind of for the rest of the talk is to kind of extend this problem a bit, where we can test between 1 and m communities or m and m prime communities. I'll show you kind of the phase diagram that we have, which more or less gives the computational line that matches the recovery line, and then I'll talk a little bit about the proof, because I think the proof is kind of cool. Okay, so the question we actually looked at was one related to this planted dense subgraph on M communities, right? So instead of just having one or two, we can kind of generalize this idea where you label the vertices, 0 through M with probability k over mn for the community ones and 1 minus k over n for the others. And then again, you connect within the communities at a higher connectivity probability than outside. And the algorithmic questions here are the same as before. Can we detect whether y was sampled from this model or a null? Can we recover the nodes from the communities if we know y is from this model? And then the question we ask is, how many communities are present? Can we learn something about how many communities are present if you just give me y? Okay, so our contribution basically says that counting communities isn't easier than finding them. So in particular, if we want to test between one or two communities like we just looked at, then this is the kind of qk squared over n line, right? And it matches the line for the recovery problem. I'll mention that we believe that the hard regime for the counting problem is exactly the same as well. We just haven't been able to formalize it. So in one direction, it's kind of obvious, right? If I have a recovery algorithm, then I should be able to detect between one or two communities, right? If I have an algorithm that recovers one community, if I run it on data that actually comes from one community, it'll find it. I know now it's one community. If I run it on a matrix coming from two communities, I don't really know what it's going to do, but it's definitely not going to find one community, right? And so the hope would be that you can you can see that it gives you some sort of garbage and know and solve this hypothesis testing problem, but we just haven't been able to formalize that within like a low degree framework or something like this.
So would this mean a harder impossible?
It means we have not. I'm not sure of this line.
That's it.
Yeah, but we conjecture that it matches this exactly. We just haven't been able to formalize it, or we didn't formalize it.
This is under the assumption that the size of the communities are same, or on expectation same.
Yes. Yeah. Yeah. So n's the same, k's the same. And then you just have Q and S, right? And, we can also, in the paper, here I'm thinking about all of the communities being the same size, so like, K over 2 or K over 3. In the paper, there's more generality, but then you have more conditions on, you can't have any one community being too small and these sorts of things. So
that's what I was asking about, because you can have that, like, when you have two communities, like the second community is irrecoverable. But once you recover one community out, the second community becomes recoverable.
Yeah. So this is something we've that our theory within the paper says, and you then just have to have an additional condition, making sure that you can't have like one of the communities like shrinking too fast to 0 or something in terms of the size, but I don't have it in the slides. So. Okay, so I just wanted to talk a little bit about how like the low degree polynomial framework works for the testing problem. So, we touched on this a little bit earlier, but kind of the idea is the following. So I want to test between a null and an alternative, and this boils down to saying my graph G, so I can think of this as my adjacency matrix, either comes from some P distribution or some Q distribution, right? It's a random graph. So, if I think of any polynomial f, taking input, my adjacency matrix, then this is going to give rise to some sort of distribution, right? Because, the G was random initially. And so what is good, right, is if we can find a polynomial such that these two distributions have means that are separated, in a way that the separation of the means is larger than the fluctuation within each of the distributions, right? So kind of what low degree testing boils down to is comparing sort of the difference in means for any kind of polynomial test F to like the maximum of the standard deviation of that polynomial, right? So, okay, so, we would say like a degree D test strongly separates if, the difference in the means is much larger than the maximum of the standard deviations, right? So we want the difference in the means to grow compared to the fluctuations. There's also a notion of weakly separating, which I'll say in a few slides, but it just replaces this, double sign with a greater than or equal to, right? So weak separation means you can still, you may not be able to find, or you may not be able to completely sort of do the testing, but you can do better than random guessing. Okay, so then, we'll say low degree polynomials fail if no degree log n test detects or strongly separates. Okay, so then the main results look like the following. So, I'm given some parameters, n, the size of my graph, k, the size of the planted structures, q, my background connectivity, and s, the elevated community connectivity. And now I want to just thinking about testing between one community and m. And the results basically look like the following. So more or less, this says if s squared over q times k squared over n is little o of 1, then no degree D test weakly separates. And then on the other hand, basically triangle counting is going to separate if you have that, this term s squared over q, k squared over n is, omega 1, right? So again, the line, that we're plotting is kind of lambda squared k squared over n, where lambda squared is s squared over q. So here, I've included D here, so, technically we're allowing D to be, grow to log n, right? So these match only up to log terms. We also included the m here, so these results are true if the community size changes with n as well. But, when I'm plotting something like this, I'm thinking of the community size as being fixed in m, but, you could also let that grow as well. Okay, so this just generalizes it, right? If I have now m and m prime, and I want to test between whether we have m communities or m prime communities, the landscape looks more or less like it did before, but now, instead of having just m here, I have things that depend on the maximum of the community size and their difference and so on. And so, I will mention that the test that actually distinguishes is just the basic sort of centered triangle counting argument. Okay, I'll mention that it's easy to extend these results to a planted dense submatrix problem. So this is very similar. I'm thinking about, I have a standard Gaussian matrix. I'm choosing, my communities in the exact same way. And then, if two nodes or if ij are both in the community, right, then I elevate their mean using now a lambda parameter, right? This is kind of a basic model for like sparse PCA and these sorts of things, right? And we get basically the same sorts of results, right? The kind of the crucial term is this lambda squared k squared over n. Phase diagrams are the same, right? Okay, so to wrap up, I just wanted to talk a little bit about a little bit more about the proof. Okay, maybe I'll mention, right? So kind of like what this seems to be suggesting at some high level is like when we're doing things like clustering or like PCA, it's like we think about algorithms and we think about like K being given to do K-means clustering or like, the number of principal components being given and then we find them with the algorithm. But what this is saying, right, is that like actually figuring out what those values should be, those parameters should be is as hard as the recovery algorithm itself. So I think it's like depressing somehow, but this is where we are. Okay, so just a few notes on the proof. I think this is really cool, and these are at least the basic sort of tools that we use in this paper are derived from a recent work by Salil Shram and Alex Wein that looked at using low-degree polynomials for actually studying the computational hardness of recovery problems. And in statistics, we often want to recover a signal, and many of these kinds of tools for studying computational hardness they're more natural to work with hypothesis testing. So I think this work by Salil and Alex is really cool, and this was the basis of kind of our approach. And so the idea is sort of the following. So, okay, so we said that, if we look at a polynomial or a test f, right, then the test is going to be good. It's going to help us distinguish between the null and the alternative hypothesis if, the difference in means that it gives rise to is larger than the max of the standard deviations. Right, and we also have a notion of weak separation where, now I just have the difference in means is greater than or equal to epsilon times the max of the standard deviations. And it turns out that how do we show something like this? Well, the thing that we actually study is this object that the low degree folks call the advantage. So the idea is that this advantage is supposed to measure kind of the advantage beyond random guessing that any given test provides. And so, what this advantage says is, okay, so look over all degree D polynomials, and you want to maximize the ratio of, the mean under P, my null, and the sort of something like the standard deviation under Q. And so the idea is that this relates, this advantage notion relates to these ideas of strong and weak separation in the following way. So if this advantage is big O of 1, so if like constant order, right, no degree test is going to strongly separate. But if, it's 1 plus little o of 1, then no degree test weakly separates. And so how do we get here, right? So I'll just sketch a kind of proof for this, right? And the proof is basically the following. So I'll do it in the case of strong separation, but the case of weak separation is like identical. The idea, is okay, so the proof says, let's assume that this is, I want to prove that if this is a big O1 quantity, then no degree test strongly separates. So I'm going to, proof by contradiction, assume not, right? Assume that I do have a G that strongly separates, and I'm going to show that there's no way that this advantage can be big O of 1, right? That's the proof style. And how do I do it? Well, without loss of generality, I'm just going to normalize my test so that it has mean 0 under Q, and then mean 1 under P, right? This is just, you can subtract and divide, and it's still a polynomial of degree D, right? And then what do we have? Okay, well, if I look at the difference in means, I've set it up such that this difference is 1, and so strong separation implies that 1 is bigger, much bigger than the max of the standard deviations, right? But now, okay, so if I look at these standard deviations, right, this is just going to be the expected value under, so for G, right, the standard deviation sorry, I think I don't need the square root here, right? So if I think about the variance of G, right, I've set the mean to 0, so it's just going to be the second moment, right? And what this implies, right, is that, I have that the max is much less than 1, so I know then that, the one for Q must be much less than 1, right? It's little o of 1, and then when you just plug this into our advantage term, you see that it has to go to infinity, right? So the idea is you can show if we do have a G that strongly separates, then the advantage is going to blow up. You can show that if you have a G that weakly separates, then you can't get the other condition, right? Okay. So then how do we actually study this object that's the advantage? Well, kind of the key point is that it boils down to basically bounding moments under these two distributions. So what we're thinking about is I'm going to represent my two models as kind of like a y equals x plus noise. So I have my output y. In the submatrix problem, it's obvious, right? I have like either this is a 0 if you're not in the same community, or an elevated mean if you're in the same community, plus the background noise. Here it's a Bernoulli thing, and what I want to test then is whether x is in is my null distribution, or x is drawn by my Q distribution, right? So if you think about this model, right, maybe P is like one community, Q is like M communities, right? So they'll give rise to different random distributions for X. And so then, what we can show is that this advantage is upper bounded by the sum here, where the elements of the sum, sorry, this should, that's an equal. This is R alpha squared. This is R alpha equal. I can't even read my own handwriting, which is not great. But what this says is the terms that you ultimately need to bound are sort of these recursive sequences on the moments under your two kind of null and alternative distributions. It turns out that like the best way to formulate this is kind of like in a graphical way. The tools that you kind of need are a lot of combinatorics and these sorts of things. But ultimately, what it boils down to is can you control like the moments under these the null and alternative distribution? Okay, I'll make this is like kind of the last thing I wanted to say, which is that I think that one of the things that we discovered here is that we believe that you can put, so one way to study the computational hardness of recovery problems is to find an equivalent hypothesis testing problem, right? So what we showed here is that if you look at recovery versus detection, so just planted versus null, right? These are two different kind of hardness, but using this sort of counting framework, you get the exact same hardness. And it turns out that I think that this can be like explored more generally. So this is a kind of this is not in the paper. This is like something we've been kind of thinking about since then. But I think it's a cool idea. So all right. So this is the object we were studying, this advantage where we want to test X, in two distributions, test between two distributions for, our signal. And Salil and Alex, in their paper, they study a similar object that is used for computational hardness of recovery. So they study an object that they call the correlation, which relates to the MMSE of the problem, and it looks very similar to the advantage. The difference is here, I have a P and a Q. It's a testing problem. There is a P and a Q. In the recovery problem, there's only one distribution, right? You want to recover a signal. And so the way that you set up kind of the low degree framework for recovery is the following. So it's Q in the numerator and denominator, but in the numerator, now we have x times f, where x is some function of the signal that we'd like to estimate for recovery. So, if you think about recovery in our problem, then perhaps, x could be an indicator as to whether node 1 is in the community, right? And so if you can study the hardness of this, then it gives you the hardness of the entire problem because of the symmetries, right? But what this suggests is a way to kind of work back and forth between these testing and recovering frameworks. So the idea is like if you're given a P and Q, then testing P versus Q is going to be equivalent to recovering the likelihood ratio when it exists, right? And so this is just kind of a change of variables here. So if the likelihood ratio exists, then testing between P and Q is equivalent to recovery of the likelihood ratio. In the other direction, right? So if you're given, something you'd like to recover, so indicator that node 1 is in my community, then using these two frameworks, what you can show is then that recovery is going to be equivalent to testing sort of the randomness, the full randomness in Y versus the randomness in Y conditional on event A having occurred, right? And so interestingly, this doesn't give rise to the equivalent testing and recovery problem we found, but it does seem to suggest that based on these two methods that you can move back and forth between these spaces, at least within the low degree framework. Okay, that's more or less all I wanted to say. Counting communities is not easier than recovering them, at least in the two models that we studied. And I believe that the low degree framework gives a way to measure hardness of recovery from testing and vice versa. And I think this could be a really interesting line of work because often I think it's hard to study the hardness of recovery problems generally. So I will stop there. Thanks for your attention.